Hello again, and welcome back to my computer vision series. Today we will have a second video about DAB Detr. This time we are going to focus on reading the code of the official implementation and actually running and debugging it. So this video supposes that you already know how DAB Detr works. If you do not, then just please check out my previous video about the actual algorithm, because we're going to use this today. In addition, the code itself is really similar to previous Detr-like models that we've seen. So the Detr itself and the deformable Detr. So please check those out too if something is not clear today. Here is the plan for today. So first we'll start with the setup, how to start model training, how to install it, how to set up debugging environment to make sure to go through the code line by line, print out intermediate variables, and so on. Then a quick recap of the algorithm itself. And then we'll go through two main parts as they are written in the code. So one part is just the DAB, dynamic anchor box creation, and the positional encodings and how they interact to have this attention modulation. And the second part is what actually happens in the cross encoder to those positional embeddings. And let's start with the setup. So to set up the training, we just clone the GitHub of the model, the official one. We install some libraries and coda layers. That is only possible on GPU. So it's not supported on CPU. It's not supported on Mac Metal Performance Shader device. So it's only NVIDIA GPU, basically. Then we need to download Coco dataset. Don't worry, it's just 20 GB, so it should be fine. And then we can just run it. So let's go through that. So I'm just going to Google DAB Detr source code. The very first link leads me to IDEA research and the actual GitHub with it. So just clone that. Then I pretty much just follow the instructions of the repository itself. For me, that worked. So they suggest installing stuff with Conda. That can be either Anaconda or Miniconda. And that is because different models might have different library versioning requirements. And so you want to have a virtual environment so that installing library for one of those models will not spoil the project of another one. So we're going to set up a new environment. So I'm creating an environment named DAB Detr 2, and I'm using Python 3.10. Then I activate it, and then I continue following the instruction. So installing the latest versions of PyTorch, Torch Vision, then actual requirements. So I'm using the pip command here. That's not usually recommended because you might have different Python versions, different PIPs that point to different locations. But in this case, I'm working from a Conda environment, which guarantees that Python and pip, they all are the same. So I'm just running pip install, and all the necessary libraries are stored in this requirements.txt file. So I'm just running that. And then I have to actually compile Coda layers, which is done with this setup.py command. It will print out some CUDA C++ warnings. Don't worry about that. As long as it's not an error, this should be fine. And then I run test.py to see if it actually worked. And we can see that tests complete successfully. So the layer installation worked fine. And now the final test fails with CUDA out of memory error, which is a slight indication that my GPU will not actually be able to run full model training, unfortunately, but I can still run for a few iterations and open the model in the debugger and actually read the code and see what happens. So now that we have set up the GitHub repo, installed all the dependencies, we need to get the Coco dataset. So I'm just going to Google Coco dataset. And the very first link leads to the original website from Microsoft. I'm going to dataset, download tab. And in here, I need to grab 2017 versions of train images, validation images, and the annotations. So you would need to download that. I have it downloaded already. So I have it downloaded and unpacked. So the unpacked folder will look like 3 folders: annotations, train 2017 and val 2017. And you need to remember this path and actually pass it to model training script. So I'm coming back to the GitHub repo. So first they suggest evaluation run. I'm going to just start with the training run straight ahead. So just copy paste this command. And the one thing that I need to change is the path to the Coco dataset. So this is the one that contains these 3 folders for train images, validation images, and annotations. So it runs, and let's see what happens. Yep, we can see that iterations has started to run. Takes quite a lot of time, but I'm not going to wait for the training to actually complete. So I'm going to interrupt that. Now for debugging setup, I have all the same stuff that was used in previous video, like deformable Detr. So I have my Jupyter notebook that I've placed right at the root of the repository, which allows me to just copy paste code from main.py, including the code that imports some of the functions defined in this particular repo, like this build DAB deformable Detr function, for example. And I can just copy paste it and execute it. Then I have my helper functions to plot the images. Then I have this special args class that allows me to sniff the actual command line arguments in the debugger, place them here, and use the object defined like that in the same way as it is used in the main.py of the repo itself. So I can just continue copy pasting code, including the code that requires command line arguments, and just execute that in the Jupyter notebook. And to actually launch the debugger, I have this launch.json script with custom args, where I have to pass all the same stuff that was used to launch the training. And then just the same code basically from the last time that loads the dataset. And once again, this is just copied from main.py of the repo itself. We can see the image shapes here. All of them are different. All of them are slightly different resolution. This is how it looks like. So you can see what transformations were applied here. So no color augmentation, no mosaic like we had in yellow, but what we call random resize crop, where you first choose the portion of the image, crop it out, and then randomly resize a little bit. And this is how the data loader looks like. So data loader is supposed to load the data into batches. But in here, the batch size is just 1, so we have 1 image. Now, the part that is slightly different to the previous code is this build model script. So this one, I copied from main.py, but basically it looks for command line argument with the actual model name. So today we are going to look at DAB Detr, which is the original Detr with queries replaced with anchor boxes. but authors of the same paper also managed to combine that with deformable Detr and achieve even better results. We will not look into that today. So now we build the model. Again, this is just copied from main.py. And now that we have the model and the images, I can just apply model to the images. And I will be able to do that in the debugger as well. So I can just press debug cell and it will start the debugger. Okay, now let's go through the quick recap of the algorithm. So this is the maybe simplified schema of what is going on. So we are mostly going to look at the decoder layer because all the changes as compared to Detr happen in the decoder. So we can think of input to the decoder as this target part and embedding part, query embedding part, and then the side input, which is just the encoder output. So for the first layer, target is just a tensor of zeros. Then for the second and so on, it will be the output of the previous layer. So instead of queries, we have what we call anchor boxes. So they act in a similar way. These are just 4 numbers for x, y coordinates, height and width of the anchor box per query. So we have 300 queries for each of them. We are going to randomly initialize trainable 4 numbers. And then we use them in a variety of ways. So the first way we use them in is this residual connection, which connects to the decoder layer output, which means that, first of all, when we compute the gradient to the loss, and the loss is connected to every intermediate layer as well. So when we do that, half of the gradient actually flows back to these randomly initialized numbers, meaning that we actually do train them in a way to represent x and y coordinates, height and width. So thanks to this training, thanks to this residual connection, we actually adjust them every time. So they are trained along the network and they are trained to represent x and y and width and height. Another way to look at that is that now decoder layer, instead of predicting bounding boxes, it predicts the difference between ground truth bounding box and the anchor it had for the current query, which I guess is easier. So you have your prior and you just predict the error of that prior for the current object. Apart from that, these same anchor boxes are used as query embeddings in the decoder layer, and we need that to modulate attention, to make sure that the attention for the current query actually does focus on the object that this query is supposed to recognize. And there are 2 main parts of it. So first of all, we have 4 numbers, so x, y, height and width. We pass all of them, expanding them into sine cosine embedding. Now that's 128 numbers per coordinate for each of these 4 coordinates. So x and y coordinates will be just fed into here, and they are concatenated with the target. So we had 256 target, and now we concatenate the positional embedding, basically. And the same happens in the side input that comes from the encoder. So we have 256 coordinates from just image content, representing the actual pixel value, and then 256 coordinates of the positional embeddings. And instead of adding them up like we do in Detr, we just concatenate them. And so when the dot product is computed, this content position embedding part gets multiplied with this sine embedding, which allows the positional embedding of the image and this bounding box prior of the anchor box to interact in such a way that the attention does get focused on the object itself. So height and width is also used in this division here, which allows to expand the attention zone or contract it or make it more wide or make it higher, which lets the model to focus on the specific areas corresponding to objects of different size and shape as well. And these anchor boxes get updated every layer. So after the first layer, we had just anchor boxes, which are independent of the image itself. Then we have our decoder layer output. We add them up, we connect that to the loss, meaning that whatever happens here is actually a good representation of the ground truth object. And then this new refined representation is used as new anchor boxes for the second layer and so on. So layer after layer, we update our current anchor box representation to make sure we modulate attention as well. So second layer will have a better understanding on where to focus attention and so on. Now let's start with the actual code. So to make it easier, I separated it into two sections. So one is basically everything that happens outside of the encoder. So how we initialize dynamic anchor boxes, how we manipulate them to make them modulate attention, and then we feed them into cross encoder. And the second part is the cross encoder itself. So how we then use these embeddings that we get from dynamic anchor boxes to actually achieve this modulated attention mechanism. And this is the simplified code structure diagram, which actually represents the Python classes used in the code. So the uppermost one is called DAB Detr, and this is basically just backbone plus transformer. So it's just a bunch of code, basically. The backbone itself is exactly the same as for original Detr. So it has code for the actual ResNet, loading the model and applying it, and it has code for positional encoding of the image. Then transformer itself is encoder plus decoder mainly, and then encoder is exactly the same as in the original Detr as well. Decoder consists of six decoder layers applied one by one, and then each decoder layer has self-attention, cross attention, and a bunch of other stuff like just dense layers, residuals, and so on. So let's start with the uppermost module called DAB Detr. And so it should just initialize anchor boxes. It calls backbone and transformers, and also it will handle residuals. We'll see how. So I'm back in my Jupyter notebook. So before calling this cell again, I'm just going to put some breakpoints. So I'm coming back to the model construction code. Right now we are reading the DAB Detr, not the deformable DAB. So I'm going here. I can see that the model is indeed DAB Detr. And I'm just going to put one breakpoint at the very beginning of the forward method. So I'm coming back to my Jupyter notebook and just call debug cell. And I can see that it stopped right where I wanted it. So the beginning of the DAB Detr class. So I received the samples, which is the nested tensor. So it will have padding, which is quite useless right now because we just have one byte size, but still, and it will have the actual images. So the type of that is nested tensor, and then samples tensors is the actual image. So 3 colors, 1063 by 736. So quite high resolution image. So then we feed that into the backbone. And let me just print the output. So the type of that is a list, although the length of this list is just 1. So if you've read the code for deformable data, for example, this is done because we might want multi-scale. We don't do that right now, but we might want that when we have different resolution version of processed images fed into the transformer at the same time. In here, we have just one scale. So we have one scale, and the shape of what we get is now slightly smaller. So it's now 36 by 23. So we downsample that by 32 times, and we get this compressed downsampled version of the image. And we have the embedding size of 2048, although it will get sampled down to 256 before we actually pass it into the encoder. So positional embedding is the same. So it's a list, and the first element has the same spatial resolution, and it's already of correct embedding size, 256. So then I have this embed weight. Embed weight is the tensor without our actual dynamic anchor boxes. So let's just bring the shape of that. So it's 300 by 4. So I have 300 queries, and for each of them, I have 4 coordinates for my anchor boxes. And this was initialized over here. So it's just pytorch.nn.embedding, which stands for randomly initialized trainable vector. And we can check out the scale of that as well. Let's print out the anchor boxes for the first and maybe the second query. So you can see that they are roughly from 0 to 1, from -1 to 1, but sometimes they go in below that. So it's basically random initialization with a mean of 0 and standard deviation of 1. All right, and that's it. So we have our embedding weights, which is now 4 numbers instead of 256 as we had in Detr. This next big call just calls the transformer. Let's just step through that. So the input to that was our 2D downsampled version of the image. Now the output is 6 by 1 by 300 by 256. So 1 is just the batch size. 6 is because we have 6 layers, 6 encoder layers, 6 decoder layers, and we want intermediate output from each of them to feed that into the loss. And then this HS is just embedding output, which has 256 dimensions. And then the reference are the original anchor boxes used in each layer. So it has just 4 coordinates. So the first anchor box is just the same anchor box that we initialized. So it is independent on the image. And then second, third, and so on will actually be updated every time we call decoder layer. Now, in the Detr itself, we just took the output embedding of dimension 256 from each layer, then applied our dense layer to convert that to bounding box coordinates, and that's it. That's our output. In here, the bounding box prediction is residual. So we have our prior, which is the input dynamic anchor box to the current layer, and the layer tries to predict the error of that. And because of that, we also return all these priors. So reference is prior, basically. We have to manage the sigmoid, unsigmoid, because we basically convert that back and forth. So we get our prior. We apply the dense layer to get 4 numbered predictions out of 256 embedding. And then we add that to the reference that we had. This shape of this is 6 by 1 by 300 by 4. And this slicing doesn't really do anything because query dimension is exactly the same. So this is just adding this, basically. And that's it. So we get our output by combining the prior, the anchor box that we had as an input with the output, and we output that. And return. And the loss is exactly the same as in Detr. So this was quite easy. But then again, we expect all the complexity to be in the transformer and down below there somewhere. Now let's go one level down. So we're not going to look at backbone, but we will look at transformer. The only thing it does is basically just call encoder and decoder and just pass around these dynamic anchor boxes. So there's not going to be a lot of code, but it's still good to read it to understand the whole picture of what is being passed around. So I'm coming back to my Jupyter notebook, back to my model building code. Here I can see that when I construct the model of type DAB Detr, I pass in the transformer. So let me just go to the transformer definition, and it uses the actual transformer class. So I'm going to the transformer class, to the forward method, and putting one breakpoint right in the beginning of it. And then I'm coming back to my Jupyter notebook and just executing the debug cell. So now I'm stopped at the beginning of the transformer code. So let me just print out all the shapes again. So SRC is now downsampled to 256 embedding size, and the spatial dimensions are of the downsampled version of the image as well. So 34 by 23. I have my positional embedding with the same shape. I have my reference point embedding, which has 200 queries and 4 numbers per query. Then I just flatten out the source. So at this point, I lose all the position information. I just basically have all my pixels in one giant sequence. So the shape of that is 782 by 1 by 256. So I flattened it out. I got like this giant sequence. Then I do similar for the mask, and then just change some dimensions a little bit. Then I use that to call encoder. And you can see here that we're not using reference point embeddings in here. So the encoder code is going to be exactly the same as it was in Detr. And the output of that has exactly the same shape. So the same 782 sequence length. Then I initialize the target. So this is the basis from which the decoder layer starts. And I just initialize it with zeros. And then I pass all of that to decoder. So I'm using positional embedding. I'm using my reference points, the dynamic anchor boxes. I'm using the memory as a side input. And I just call the decoder. And the decoder shape is exactly the same as we've seen before. So for each of the 6 layers, I get 300 query outputs. So the main output is the embedding. And then we also have references, which store the initial 4 numbers that were used as anchor boxes for each of the layers. Okay, now let's move even deeper. So we're going into the decoder now. So as I said, encoder is exactly the same as in the base Detr model, and then decoder will have a lot of stuff. So this is like one of the 2 key parts of the model, and it does all the setup for dynamic anchor boxes. So it takes in the 4 numbers, expands them into sine cosine embeddings, performs the positional and scale modulation, scales overall positional weight, and handles residuals. So let's dig into that. So I'm coming back to the transformer.py file. So it has the transformer model and all the components as well. So I'm interested in transformer decoder. So I'm going to the definition of that. And once again, just putting the breakpoint at the very beginning of the forward method. And I'm back in my Jupyter notebook, and I'm starting to debug the cell. So let's just confirm all the input shapes once again. So the target is 300 by 256, and it just all zeros for the first layer. And then for the layers after that, that will be the output of the previous layer. So the memory is the encoder output, and it has this different image-dependent sequence length. And then I also have the positional embedding from the content of the image with the same sequence length. So let's iterate further. So I'm starting with the first layer. And once again, this slicing doesn't really do anything. So I'm basically getting these 4 numbers for each of the 300 queries. Then I am generating the sign embed. So let's dig into that. So here is the slide reminder from the previous video. So let's say I have my positional coordinate, so the position number 1, 2, 3, and so on. And then the y coordinate will correspond to coordinate within the embedding. So for each of the x, y, height, and width, I would have 128 coordinates. And so we can say that at least how it was in the positional embedding for the image, we could say that the first coordinate of this encoding will be a sign function, the most frequent sign function that changes a lot. Then the coordinate above that will be slightly slower. And then the final one will be really, really slow, so you can hardly notice what is changing. And so every position in the input gets expanded to this 128-dimensional vector. So this is the picture from positional coding for the image. The thing that is different for the query is that now, instead of first element having the position of 1, then 2, then 3, and so on, instead, each of them just have random positions because we initialized x and y and height and width as random numbers. So there will not be this cute picture that looks quite symmetric and so on. Instead, every element will have completely different random initial position, but it does get expanded into this embedding in the same way. And the code for doing that is pretty similar. So let's get here just to print out some shapes. So we get these 300 by 4 numbers. We choose the scale. So the scale is the frequency of the fastest sign, and it's exactly 2 pi. So it goes up, down, and it stops here. So it's exactly 1 period of the sign function. Then I have this temperature of 10,000. And then let's see. And then so at this point, pos x already has the same shape, but so it has 128 numbers per query. And then I'm taking the sine and cosine parts of it. So this is exactly the same as we did for the image. And we're doing it here for x number, for y number, and then in a little bit for width and height. And we return the concatenated version of all of that. So basically this final position will have the dimensionality of 512. And so the first 128 will correspond to the y coordinate, second 128 will correspond to x coordinate, and so on. So I'm back in the decoder layer forward code. So I just expanded my 4 coordinates per query into these positional embedding. So now we have 512 coordinates per query. And then I will basically construct 2 objects. So one object that is called query position here, it will be fed in directly into the layer, and the layer here is the decoder layer. And then another one called query sign embed is also passed into the decoder. And so if we come back to the overall diagram of how it works, so this query sign embed is basically the positional part that will interact to the corresponding positional part coming from the encoder. And then what is called query pos here is basically taking this sign embed, projecting it using some dense layers, and just adding them directly to target. So we'll see the addition part when we get to the actual decoder layer. But for now, we'll see how we get this sign embedding and how we project it down here. So now I have my query sign embedding. I have my ref point head. which is initialized as MLP. And the output of that is this query pos object. So basically, I started with 512 coordinates corresponding to x, y, height, and width. I projected it down to 256, but this also means that this query pos has information from both coordinates and height and width of the anchor boxes. And then this object gets passed to the decoder layer without modification. Then I have my positional transformation. So positional transformation is just a number, right? So it's just one number per the entire layer. So initially it was just one, and for later layers, it is just trainable. But once again, it is just taking the layer ID. So it's basically one trainable number per layer, and we multiply our positional embedding by this number. So this lets the model control how much attention to pay to positional information for each layer, and sort of modify the scale of this positional contribution in the attention. Then I iterate forward. Then I have my reference coordinates. So we are looking at this division part here. So now I had my x and y coordinates, and I also had height and width. So I use height and width for modulating the scale and shape. And I do that by taking some predicted base height, let's call that H1 and W1, and I divide that by the actual anchor box heights and anchor box width. And then I get two coefficients, and then I just multiply this entire embedding, the x and y part of that, I multiply it by these coefficients. So ref anchor head is once again just the bunch of dense layers. So MLP stands for multi-layer perceptron. So I'm taking my output. So let's recall the shape of that. So output is what we called TGT or target previously. So it's initialized with just zeros. And then for the next layer, it's going to be the output of the previous layer and so on. So I use that, I pass that through a bunch of layers to get my reference height and width. Right, so height and width, that's just two numbers for every query. And then I take my query sign embedding, and this slice is basically taking the x coordinate of that. The shape of it is now 128. And then this one is also 128 shape, but that should stand for the y coordinate, because this one is equal to 128. Basically, this one is taking first 128, and this one is taking second 128. And so I'm taking this part of the query embedding. No, sorry. So I forgot to mention that by this time, we already cut off half of it. I guess this is really important. So in here, we started with 512, which stands for expanded position embedding for x, y, height and width. Then in here, we cut off half of it. So we cut off the first 256 coordinates. So cut off, leaving just x and y embeddings in place. Then we take x embedding and divide it by the width, multiplying by this reference width that was predicted based on the actual input to the decoder layer. And we take the y coordinate and we divide it by the height of the anchor box and multiply it by this reference height that we got from decoder input. And that's it. So after this, we are ready to pass that into actual decoder layer. So there will be a bunch of logic there as well. But for now, we are basically, we have our output, which is just zeros now, and it stands for like content part of decoder input. We have signed input called memory coming from encoder. We have positional encoding also coming from encoder. And then we have two parts of this query embedding. So one called query pos that has information from both x, y, height, and width. And then this query sign embedding that only has information from x and y, but then it was also modulated by dividing by this height and width. So it should be wider or smaller depending on shape and size of the object. And that's it. So now we call the layer, and this code will be pretty similar to in all the layers. And now the final part that we need to do here is the residual. So the output of that is the same shape as the target, so 256 coordinates per query. Then we have this bounding box embedding, which is again just MLP, so a bunch of dense layers, to take this embedding output and project that into the actual bounding box coordinates. So it's 4 numbers per query. Then, once again, this slice is not doing anything, but I also add this inverse sigmoid from reference point. So this is the part where I do my residual. So I had my initial priors for the bounding boxes. So I had the anchor boxes. I have my layer prediction, and the final output of that layer is the sum of these two. So basically, the layer tries to predict the error between the anchor and the real ground truth bounding box. Then I initialize these new reference points as just the same output I had just now. So ref points is a list that I will return in here, right? So this is the list with all the anchor box inputs for every layer. And I'm appending, so I appended the initial anchor boxes here, and then for every new layer, I'm appending the input to the next layer, basically. And then I have this detach call. So this is also quite interesting. So now this reference points object is going to be used on the next iteration when we look at the second layer, third layer, and so on. And at this point, we call detach, which basically stops the gradient flow through this node in the graph, which is the same as saying that for the first layer, when we compute loss gradient, the gradient does flow to the initial anchor boxes. But then after the first dynamic update, when I have these new anchor boxes, they are going to be detached. So whatever it is the loss was for the next layer, it is not going to flow through this node. So only the first layer actually affects the training of the initial priors, which I think is really important because we want them to actually represent height and width of the objects. But then the gradient doesn't flow from further layers. And that's it. So I get my layer output, I handle residuals, I save all the intermediate outputs, so the actual embedding output of the layer, and the input reference points, and just return all of that. Okay, now that we've looked at how anchor boxes are created and expanded into positional embeddings and modulated using coordinates and size, now let's look at what actually happens to these embeddings in the decoder. So we're moving down one layer from decoder to decoder layer. In there, we'll see how self-attention works, how cross-attention works, and how the different versions of the query positional embeddings are used. So query pos that depends on all 4 coordinates, x, y, w, and h, and the query sign embeddings that only depend on x and y coordinate of the anchor box, but it is modulated using height and width. So I'm going back to my Jupyter notebook. I go to my transformer.py code and then find the decoder layer class definition. So I go to that and then just put one breakpoint at the very beginning of the forward method. And then I execute the debug cell. So I've stopped it here at the forward method. Let's just confirm one final time the shapes of all the inputs. So the target is the content part of the decoder, and the query positional embedding will be the positional part. So it has the shape of 300 by 256, although all these coordinates are initialized at 0. Then I have my position. So position is the positional encoding from the image itself. So in here you can see that the sequence length is 782. And then I have two versions of positional embedding for query. So both of them should have the same shape. So query pos depends on all 4 coordinates, and then query sign embedding depends on just x and y, but it is modulated by height and width as well. So first we have self-attention. So let's look at the call first to understand it better. So this self-attention is defined here. It's just PyTorch multi-head attention. So it's the classical multi-head attention module, not modified in any way. And it is called using query key and value. So value just comes from the target. So this is self-attention. The self-attention only looks at stuff that comes from the query part. So it's not dependent on the image itself, for the first layer at least. And then we have query and key. So the query and key will actually be used, the dot product between them will be used to compute the attention weights. So I get my target, I get my query position encoding, I project that down one more time using a linear layer just to be safe. And I use different linear layers to get the query content and query positional part, and then key content and key positional part. So the content part comes from the target, positional part comes from this query pos. Then to get the final query and key, I just add them up. So at this stage, it's similar to how it was in Detr, where I take the content, I take the positional embedding and just sum them up. And I pass that into self-attention. And once again, we can see here that query and key depend on the positional embedding, and then value does not. Let's go through that really quickly. And it is done. So now this target 2 is of the same shape as the input. So we got our input queries and target, that is just 0, but still we got self-attention to make these queries interact with each other to refine the information between them. Then as usual, I have dropout, I have residual connection, which is this plus sign here, and normalization. And then I move on to cross attention. So for cross attention, things are going to be a bit different. So I also have queries, keys, and values. Now only queries come from the actual query part, and then keys and values will come from the content part. And now both of those will have the content and the positional part. So the query content basically depends just on target. Then key content depends on memory. So the output of the encoder value again depends on memory, using and I just project them using some dense layers once again. Then I have this key positional part. So key part comes from the image, from the content, And the positional part is the positional representation of a pixel within the image. So then, once again, I have my query positional embedding for the query. I project that one more time just to be safe in the different version of query positional embedding. I add that to my content query. And then I do the same for the position part, for the key. And then something different happens. So up until now, this looked similar to how it was in Detr and how it was in self-attention. Now I grab my query sign embedding. Now this is the part that only used X and Y coordinates of the anchor box. I project it one more time, and then the final query I get from concatenating the initial query that I had was this query sign embedding. And I do the same for key. So key comes from here, and it was again positional encoding plus content. But then I also concatenate key positional embedding to that. And so query shape is now twice the size it was. So it's now 512. And so is the key shape. It's also 512. So basically, both query and keys, they are going to be multiplied. The dot product between them will be used to compute the attention weight. And when you compute dot product, you basically do element-wise multiplication. So now both query and key basically consist of content part concatenated with the positional part, although there is like a positional component that was also added to the content part. And thanks to this concatenation, when we compute the dot product, we multiply the positional embedding of the image by the positional embedding of the query, which is exactly the thing that makes the attention modulated. So sine and cosine embeddings work in such a way that when the query position and key position were the same, the multiplication is maximal. And then as soon as they start moving apart, so as soon as the position changes, the dot product decreases basically, which is the thing that is saying that if the object is located here, then the attention will be focused here. And as we move away from this point, the attention is going to decay. So this is like the main insight about the model, basically. We can also notice that now the cross attention in the decoder is twice as big. So we have the twice embedding size because of this concatenation. But then it's still less, it's relatively small contribution because cross attention operates on the query sequence, which is usually smaller than the image sequence. So the difference is not that big. And so to recap, we had positional embedding from the content that we used two times. So one, when we just added that to the content embedding, and the second time when we concatenated that to the content part. And for the query, we had two different tensors. So one that's called query pos that was added to the content part, and it has components for X, Y, W, and H. And the second one that is concatenated, which only had X and Y components. So now we have all that. We provide the query, the key, the value. Once again, the value does not have any position encodings in it. And I just compute cross attention, which is again just the same multi-head attention layer from vanilla PyTorch. And that's it. So now I get my output, I get my residuals, normalization, activation, linear layer, dropout, all the usual stuff. Okay, so that was it. That was the entire code for dynamic anchor boxes. It's really quite a simple concept once you understand how all the parts connect. So we have just 4 randomly generated trainable numbers that represent the coordinates and the size of the object. And then we pass that through the residual connection to make sure they actually are trained as not just random numbers, but position and size. And then we expand them into sine-cosine embedding, and then to have that as a dot product within the attention calculation in a smart way to make it like modulation of position. So this was it for today. I also want to mention that I have my channel about computer vision, about machine learning in general, which I hope can be not just a collection of random videos, but actually a learning path. So right now I am focusing on modern object detection. So I started with YOLO and Detr models. I described how they work. I've read the code for both of them. And then I'm trying to read through modern papers that improved upon these concepts. So deformable Detr, DAB Detr, again, reading code for all of them. And the next one I'm going to do is the denoising Detr, which is yet another step on the path towards current state of the art. So current state of the art called CoDetr, it's based upon slightly improved models like Dino, with backbone replaced with swing transformer or vision transformer. So we are going to talk about all of that. The very next one will be about denoising Detr. In addition to that, I have a beginner course. So it starts with something really simple, digit classification with PyTorch. You can just do it on your laptop, sit down in half an hour and have a video explaining all the steps. Then on top of that, I have a lot of videos adding some advanced concepts of deep learning, basically. So initialization, activation functions, convolution, cross-entropy loss, Bayesian normalization, all of that stuff. And that culminates in a big project called Training ResNet Network on ImageNet dataset. This is a code read and benchmark implementation of the famous ResNet network that is used as a backbone in the current model, but back in 2015, that was the first model that could beat human performance in image recognition. So it's quite famous. On top of that, I have started a branch about generation, about GenAI, basically. The very first video is already out, and it is about neural style transfer, which is quite simple, but a cool technique. And then I'm hoping to build on top of that to talk about autoencoders, diffusion, stable diffusion, GANs, and interesting stuff like that. So, hope to see you soon.